Welcome to the first part of a two-part lesson on cross products of vectors. Prior to this lesson, you should be familiar with vector operations and dot products. Let's say you're trying to turn a nut using a wrench, and the distance that you're pushing away from the center of mass of the nut is represented by delta D, and the force that you're putting on is represented by a vector, a force vector. Torque is the ability of a force to cause a rotation. There's a few factors that affect this. One of them is how far away from the center of the mass of the object you're actually putting the force on. So if the displacement vector increases, then the amount of rotation or the ability to cause that rotation also increases. Also, the amount of force that you're putting in. So the more force you put in, the more ability you have to cause a rotation. The other main factor that affects how much rotation you can cause by a force is the angle between the displacement vector and the force vector. If your force vector is in the same direction as your displacement, then you're not causing any rotation. But if your force vector is perpendicular, then you can cause the maximum possible amount of rotation based on your angle. So that means if we want to calculate the amount of torque done when we're putting a force at a displacement, then we have to find the perpendicular component of the force acting. So in this case, with this angle, it's going to be F times, or the magnitude of the force multiplied by sine of theta, and multiply that by the displacement. So the torque equation is going to be the magnitude of the force multiplied by magnitude of the displacement multiplied by sine theta. Torque is often measured in Newton meters, force is measured in Newton, and displacement's fundamental unit is meters. Now, torque is a vector unit, and it will allow us to get an understanding of which way the nut, in this case, is actually turning. So this vector is perpendicular to both the force and displacement vector. We'll talk about how to find a direction a little bit later. But when we point our thumb towards the direction of this vector, then the way that our fingers are curling will show us the rotation of the object, in this case the nuts. So for the equation represents the magnitude of the torque, but to get its direction, we can represent that by a unit vector n, sometimes unit vector u, and this unit vector is perpendicular to both the force vector and the displacement vector, and it will allow us to get an idea about which way the rotation is actually happening. Multiplying two vectors like this is so common in both physics and math that we have a whole way of representing it. We use torque is equal to F cross delta D, which is like a multiplication sign, and this is what we call the cross product in vectors. Therefore, a vector product or a vector cross product is a vector that is perpendicular to both other vectors. And if we had vector A and B, their cross product will equal to the magnitude of vector A multiplied by the magnitude of vector B multiplied by sine of the theta, the angle in between them, multiplied by a unit vector n, which represents the direction of this vector, and this direction is perpendicular to both vectors A and vectors B. Imagine we were to take the cross product of vectors I and j. Vector I represents a unit vector in the x direction and j is in the y direction. If we wanted to find the cross product, we have to use our right hand or a right hand rule, where our index finger represents the first vector being multiplied, our middle finger the second, and the resultant would be the direction of our thumb. And you can see that here I and j are represented, and the resultant vector is perpendicular to both of those vectors. And then we can use we point our thumb towards the direction of the resultant vector, and the way that our fingers curl is the direction of possible rotation. Let's look at the cross product of unit vectors k and I. We do the exact same thing. K points, let's say, out of the page here, and I in the x direction. Then we point our index finger towards k. our middle finger towards I, and our thumb will be the resultant vector, which is pointing in the Y direction in this case, and our rotation is which way our fingers are curling. To summarize, whenever we want to figure out the direction of the resultant vector from a cross product of two vectors, we use the right-hand rule. So if we want to take the cross products of vector A and B, index finger represents A, middle finger represents B, and the resultant vector would be our thumb. If we want to figure out the direction of the rotation, then we point our thumb towards the resultant vector, and the way that our fingers are curling will be the direction in which the rotation is happening. Now let's look at how we can determine the cross product of two vectors given their components. We're going to let V be the cross products of vectors A and B, and because of this we know that vector V is perpendicular to both vectors A and B, and that means the dot product of vector A with A and B is going to equal to 0. The dot product of V and A is VxAx plus VyAy plus VzAz, and that's going to equal to 0. And the dot product of vectors V and B is VxBx V plus VyBy plus VzBz, and that also equals to 0. Now, putting all these together, we can actually solve for vector V, and we get its x components as AyBz minus AzBy, its y component as AzBx minus AxBz, and the z component as AxBy minus AyBx. The derivation of this is not provided in this particular video just because of the amount of time and space that it actually takes, but if you want to see it, please leave me some comments, and maybe I can provide this in an alternative video. Now we can see that the components are kind of strange, and the derivation actually takes too long, so you can't just do the derivation every time you're trying to come up with the equation. So we're going to look at an alternative way to kind of help us with figuring out the cross product between two vectors. So let's take cross products of A and B. So we're going to start off by drawing a big line brackets, and we're going to put components I, J, and K, and we're going to put the x, y, and z components of vector A first, and then the x, y, and z component of vector B. Then we're going to use a positive value, and for the x components, we're going to cover up the top row and the I row, which is for x components, and we're going to write everything else left, which is AY, AZ, BY, BZ. And then for the y component, we're going to do the same thing. We're going to use a negative this time, negative j. We're going to cover the j column and the top column and write everything else, AX, AZ, BX, BZ. And we're going to use a positive again for the z component. So it's going to be unit vector k multiplied by, we're going to cover the top row and the k column and write everything else. That's AX, AY, BX, BY. For using the cross product using this particular method, we have to use positive, negative, and positive for the x, y, and z components. The cross product then ends up being the x component, and to find the x component we draw diagonals, the diagonals from top left to bottom right first, so AyBz subtracted by diagonals from top right to bottom left, and that's going to be our x component. We're going to subtract that. We're going to use this exact same concept, the diagonals from top left to bottom right subtracted by diagonals of top right to bottom left. And then for the z component, we're going to do the exact same concept. It's going to be the diagonals of top left to bottom right, subtracted by the diagonals top right and bottom left. And using this, we can find the x, y, and the z component of our resultant vector. The summary of this video is provided here, so if you want to pause and write them down, please feel free to do so. And now we're going to look at a few examples. For the first example, we want to show that the cross product of the unit vectors j and I is equal to negative k. We know that the components of unit vector j is 0, 1, 0, and components of unit vector I is 1, 0, 0. And let's just take the cross products. We're going to draw our brackets and we're going to put components I, j, k. We're going to put the components of vector j first as 0, 1, 0 and components of I as 1, 0, 0. For the x component, we're going to cover the I column and the top row, and we're going to subtract diagonally 1 times 0 minus 0 times 0. For the y component, we are going to cover the j column and the top row, and we're going to subtract diagonally 0 times 0 minus 0 times 1, and we're going to subtract is minus j. And for the z component, we are going to add the k components, and we're going to cover the k column and the top row, and it's going to be 0 times 0 minus 1 times 1. Putting everything together, we get 0i minus 0j minus k, and in this case we do get a negative unit vector k as our final answer. For the next question, we want to determine the unit vector which is perpendicular to vector a and vector b. What we're going to do is we're going to take the cross product first and then take the unit vector afterwards. So for the cross product, we will write all the components of vector A and vector B first. And then for the x component, we're going to do I, cover up the I column and the top row, and use the diagonal multiplying method to get negative 1 times 0 minus 2 times negative 1, and then minus j. Meaning we're going to use everything but the j column in the top row. So that's 3 times 0 minus 2 times 1. And for the k components, we're going to use positive, and we're going to use 3 times negative 1 minus negative 1 times 1. Once we add and simplify everything, we'll end up getting 2i plus 2j minus 2k as our final answer. Now, we know that the cross product has x, y, and z components of 2, 2, and negative 2. So to get the unit vector, we need to take that and divide it by its magnitude. The magnitude is the root of the x component squared plus y component squared plus the z component squared, and that will end up getting us root 12 or 2 root 3. Once we have that, we can start dividing each individual components by the magnitude. So we have 2 divided by 2 root 3 times I plus 2 divided by 2 root 3 times j minus 2 divided by 2 root 3 times k. We divide everything by 2 for each component, and we get 1 over root 3i plus 1 over root 3j minus 1 over root 3k. And if we rationalize our answer, we get root 3 over 3 times components 1, 1, and negative 1. For the last questions of the day, we're going to have Robo, who exerts a force F on a nut at a displacement delta d from its center of mass, and what we're trying to figure out is we want to determine the magnitude of the resultant torque. Well, we know that the resultant torque can be calculated by the cross product of the force and the displacement, so we write everything out. We write all the components of force and the displacement, and we use our diagonal multiplication method for each component, and we use positive x components, negative y components, and positive z components. And once we put all our numbers together, we'll end up getting x component of negative 8, y component of negative 11, and a z component of positive 2. Now we want the magnitude of the torque. We don't need its vector component, so the magnitude is the root of x component squared plus y component squared plus z component squared, and that simplifies to 3 root 21, or approximately 13.7 Newton meters in 3 significant figures. I've left you with 3 practice questions, and I will try to post a full solution to these in a separate video as soon as I can. I hope that this video was helpful in giving you an understanding of the basics of the cross product, and the second part of this video, which will be posted later, will focus on properties of the cross product. Thank you for watching.